Okay, so so let's go through the new property again, just because I guess that was probably a little bit quick last time. So remember, what happens is that the threshold row tells us how hard or how difficult to satisfy a constraint is. So having a large value of rho means that the constraint is very difficult to satisfy. So this piece here, right? On the other hand, it also means that it'll actually decrease the value of the objective function quite a bit. So it's in our interest to have a large value of rho. At the same time, it's in our interest to have a small value of psi. But those two things are in conflict, right? So the idea is basically to scoop up as much of that margin through rho while not having too many of those slack variables psi I kick in. Because I have to pay for those psi i's only whenever they are really non-zero. If I'm away from the boundary, I don't have to pay. So if you think about this as being the boundary, and these points here, they don't really matter very much. Whereas on the other hand, those points there, they matter because if I change my margin, things will actually, so this is basically what I can affect with rho. This is what's going to affect those slack variables. Right? So these are the only ones where I have to pay. So if I make rho larger, that means I'm pushing the boundary outwards, right? Then these terms here will increase. And furthermore, the points that are directly on the boundary, these points here, they will also start kicking in. So in other words, if I'm increasing rho, then I basically have to pay fractionally for the points that are on the wrong side of the boundary, plus the points that are exactly on the boundary. Whereas when I'm decreasing rho, the points that are on the boundary, they don't really matter. I benefit only from those that are on the left side. Now, if I have to assume that we have optimality in all the parameters, it basically means that the fraction of points on the left side and the fraction of points on the left side plus those on the boundary are going to bracket the interval that contains nu. You can check that. So, and there's some delay in the display. Yep. So basically, what happens is, since you need to, if you make the threshold smaller, you benefit only from the points m minus, which are those here. Whereas if you make the threshold larger, you have to pay for all the points m plus. Then putting both inequalities together gives you exactly this, which is exactly what I told you. So by and large, modulo the points exactly on the boundary, nu tells you the number of points that will be considered as novel. You can use the very same trick also for support vector classification and regression. So you can say, for instance, for support vector classification, I want to train a classifier that has maybe 5% or 10% margin error. That's actually quite convenient because quite often you may have some idea of what error rate you should be able to expect from your classifier, right? So at least you have some idea of what error rate would make you really happy. This lets you actually set this number beforehand and then just say, well, pick the regularization in such a way as to get that answer. Formally, the two things are equivalent, but it simply means that you don't have to go and manually tune C, because C is essentially now part of the optimization problem. That's effectively what happens here. Okay. Okay, good. And then just to show you a toy example, what basically happens is, depending on whether you pick nu to be really large or really small and so on. I mean, and basically depending on how smoothly you pick things, you will see that different sets of points are considered novel. Okay. Now that's all very nice in a toy example, but let me show you something. Yes, somehow Keynote has problems with large files. On OCR. So these are the same digits that we saw last time when we looked at them using parse and windows. Yeah. Okay. So what happened basically when we used parse and windows, we got ugly looking digits, but they weren't really horrifically ugly. Now for those top 20 that you see here, I think it's quite hard to argue sometimes what those digits should be, right? So the first one, okay, maybe you could say it's a 9, but you could also say, well, that was probably just a 0 badly written. The second one being a 1, okay, it's a European one, and given that this is a US data set, European ones are less frequent, which probably makes a lot of sense. The third one, I think, is just garbage. The fifth one, well, okay, it's a European 7. Again, it's an American data set, so Europeans are infrequent and are novel. Then, if you look at this guy here, it's clearly a missegmentation. This is equally garbage. This I would actually view as a 4, right? That this should be a 5, well, I don't know. I could equally well see it as an 8. That this is a 0, well, I don't know. So basically, and that this is a 6, well, I have no idea what it really is. So basically, what you can see is novelty detection is actually a little bit better than just using parse and windows and then thresholding. The main reason for that being that novelty detection will explicitly optimize for the regions of low density as opposed to just trying to do a good overall density fit and then solve the problem. Now here's an interesting thing though. So when we did this, well, we ran novelty detection on USPS, and then we thought, okay, yeah, so these are the really, really ugly data points. Let's throw them out. After all, I mean, this is clearly garbage, so this can only hurt. And we thought, okay, by removing the worst data points from the training set, we should actually be able to get a better classifier. We were so wrong. So quite surprisingly, removing those from the training set actually made our classifier slightly worse. The reason being that some of those are essentially boundary cases. And by having more data on the boundary, you will actually sometimes end up with a better classifier and overfit less and so on. So it's not always clear that database cleaning will really lead to better classification. Okay, so this is just as a cautionary note. That's it. For instance, if these are network traffic behaviors, then it's very clear that a novelty detection will beat something that just models the density. Okay, and then just to give a last example about the new trick. So what you can see here is that essentially, depending on how aggressively you change the kernel width and the threshold, you will actually get very different solutions. So it's the same data in all cases. But what happens is basically as you change new, sorry, Keynote is acting up. So basically from left to right, what you see is a change in the value of new. And on top, actually let me ask, who thinks that the top kernel is smoother than the one on the bottom? Who thinks that it's narrower than the one on the bottom? Okay, I guess everybody got the intuition right. So this is a very narrow, non-smooth kernel up here. I don't know, let's say sigma squared equals 1, and maybe here we have sigma squared equals 10. Doesn't like this slide for some reason. And if you change nu, well, here it would be probably in the order of 0.5, and here it might be in the order of 0.01. Right. So as I increase the size of the margin, as I allow more points to be novel, of course, the novelty detector has to work less, and you get very simple solutions out of it, right? But it also means that, basically a lot of points in here are considered novel, right? Okay, so I guess we've done enough novelty detection. Let's look a little bit at optimization. Any questions so far about novelty detection? Okay. Actually, more to the point, what we're going to do is we are going to skip the convex optimization part directly, but we will go into a specific form of kernels, and because it's actually a rather useful one. So what happens is, in many cases, you actually end up with data that is already very, very high dimensional to begin with. For instance, if you want to do personalized spam classification, you actually have all the tokens that occur, and then you also have the users. And in some cases, that already, in its own right, is so high dimensional that you cannot entirely fit it into memory. So that's obviously not a very good situation. So you want to ensure that you can still make things fit into memory, because when you work in a company and you say, well, can you please buy more memory for the machines in the server centers, people will just laugh at you and tell you to go away. So you can't. So what we're going to do is we're actually going to look at a specific problem where this occurs. So we'll see something that's called multitask learning. And then we'll actually see how to address this efficiently. Okay. So let's start with a practical example. So a colleague of mine who was a co-author on that project, so he got some email. And the question is, is this email spam or not, right? And yeah, I guess if you squint a little bit hard, you'll see that this is spam. And now let's assume that he's not the only one. So Kilian by now is a professor, I think, somewhere in the Midwest, in St. Louis. Anyway, so suppose that he's not the only one who gets this email, but there's maybe, 5 other users who get this. And so the unfortunate thing is that, well, you would expect that all the users would actually go and do this. Yeah, but that's not quite the case. What you actually sometimes get is that people maybe think that they actually want to get Vicodin, Xanax, and so on. So maybe he thinks it's a quality email. And Homer's just confused. And so there's not much you can do. What you also get, and that's quite a problem, is spammers can also label their emails, right? So they can also label their emails at actually a low price. So if you want to know how much this stuff costs, you should go to a website called freelancer.com. And this is a place where people post a variety of IT jobs. And some of them are simple, like, I want somebody to set up my website, okay? Or, design me a nice logo. And it gets to the, I need 10,000 Facebook likes for my product, to the sad and bizarre of the form of, I need 10,000 votes for me being the best DJ in the next competition. I've seriously seen this. So it's kind of sad. And then the criminal, which is, well, hey, I need 10,000 or 100,000 email accounts from such and such a provider. And then depending on the provider, the price is different. So can somebody guess which ones the most expensive accounts are right now? Yes? Gmail is expensive, but it's not super expensive. I mean, yes, it's more expensive than Yahoo and AOL. Sure, we all know that. But there's another one that's way more expensive. It's not directly an email account, but it's an account nonetheless. Yes?
Something related with .gov?
Not quite. So actually, Craigslist is really expensive. So the reason why Craigslist is so expensive is because they do phone verification. And that phone verification makes it a little bit more painful. So at some point, those accounts were going for 50 cents a piece. The price has probably come down now because you can easily spoof phone numbers, but yeah. So, fun? Apple? Apple IDs, I don't know. You can look them up right now. So just go to freelancer.com, search for Apple ID, and you can tell us the number probably in a minute, what the going rate is. So the point is, spammers also label. And you might think, well, okay, we can fix that by forcing people to, register with a credit card. They also steal credit card numbers, right? So it doesn't really help very much. The much more common problem is this one here. A lot of users don't label their email as spam or ham. Who of you has labeled an email as ham and spam in the last week? Wow, that's impressive. That's probably as high as I've never seen it before. Yeah, CMU rocks. Okay. Usually I see 1 or 2 hands going up, so this is good. You're not only doing everybody else a favor, you're also doing yourself a favor. So please keep up the good job. And I'll show you pictures why you're also doing yourself a favor with that. So this is awesome. Usually you get 1 or 2 hands going up. Right. So, and given that you have all those users, you want to do spam classification, and you still actually want to make sure that you catch the spam. So how can you do that? So one option is simply, well, you give each user his own classifier, right? You could do that. And if you did that, well, it would be very easy, right? So we train a classifier for Homer and one for Marge and, one for all the other characters. But here's a problem, right? Because most users don't really label very much data. So the classifier would be really bad. So one option is to say, well, let's actually have a personal classifier for each user, which corrects a global classifier. So we have basically a large number of tasks. Each user corresponds to his own task. And I'm assuming that all those tasks are quite correlated insofar as they deviate only slightly from the global task. You could actually do more intelligent things by saying, well, and these deviations are also all correlated. And you could model that. So that's another fairly interesting thing that you could do and probably should be doing nowadays. But that's this simple model that we had, and I'll walk you through how it works. So basically, we now have one classifier per user. We have a global classifier, and we need to store all of that in memory, right? Which is going to be fun. So let's say we do that. So we have basically our email, and we have a common parameter vector, and we have a user-specific one. So in that case, the decision function f of, email and user is just whatever features I managed to extract from the email applied to, some parameters that are common, then I have a user-specific part, right? And all I'm doing now is I'm rewriting that as an inner product between some other feature map and some other parameter w tilde really. Okay. So what I'm simply doing is I'm mapping things into some higher dimensional space where I'm taking the vector that is given by basically 1 plus e user. So this vector looks as follows. It's basically a 1 here, and then they're all zeros. Then I have a 1 for that user, and then I have all zeros again.
What is?
Pardon?
What? Can you explain this?
Yes, I'm explaining it right now. So 1 plus e user is this green bit here, right? So this vector has a 1 in the first coordinate, and if you use a number 42, it has another 1 at coordinate 42. And if I'm user 1001, in my case, this would have a 1 at coordinate 1001, and zeros all elsewhere, and a 1 in the first position, of course. Okay? So I basically have now this vector, which is 1, and then lots of zeros, and somewhere where that user ID is, I have a 1. Got it? And I'm taking the tensor product with w. Sorry, apologies, with x. So what that really means is that I basically write the features of the email, in a bag of words representation first, then lots of zeros, and then when my user ID occurs, then I basically copy all those instances again. And this is just a less awkward way of writing this. That's basically this term here. So phi of x is this thing here, and 1 direct sum plus EU is this thing here. And you can check that with a suitable w tilde, you actually recover exactly the representation that we had before. Because my w tilde simply scoops up all the parameters for all the users and also the common term. So the common parameters are basically the first set, then come all the terms for user 1, then all the terms for user 2, then all the terms for user 3, and so on and so on. Okay. Does that make sense?
So there is only one classifier.
So now I have only one classifier for all the users, but I end up with an absolute monster of a parameter vector. So I've basically turned it back into a regular classification problem. Before that, we had a multitask problem where we had highly related tasks, and all I'm saying is, well, let's model those related tasks as a common task plus then a lot of things that deviate from that common task. Right? That's essentially the idea. Any questions so far? Okay. Okay, good. So now what I can do is I can just compute the kernel between the email user and email user pairs, right? So k of xu, x prime u prime, well, all I have to do is just take that inner product. Let me actually do a little bit of algebra here, because otherwise it's kind of not so much fun. So first of all, this assumption that the user parameters are essentially just a deviation from the common parameter means that we have basically here our common parameter w, and then for each user, maybe w Alex, maybe wj, and whatever, all of those might deviate only slightly, maybe some a bit more than slightly, from that common parameter. So that's the assumption. So that's essentially by what I get by assuming that my personal model is W plus W Alex dot phi of x. Now what I've simply done is I've rewritten that into some W tilde and phi of x. Let me use a more readable thing. W tilde dot phi of x tensor product with 1 direct sum plus E Alex. Okay. Now, if I want to take this thing here, which I can treat as phi of x and u, and take the inner product between phi of x and u and phi of x prime and u prime, that's of course nothing else than the inner product between phi of x tensor 1 plus EU dot phi of x prime tensor 1 plus EU prime. And we know that this tensor operation gives me products of the kernels. Right? So this is nothing else than the inner product between phi of x and phi of x prime times inner product between 1, it's direct sum, sorry, EU and 1 EU prime. But I also know that this direct sums are just sums of kernels. So 1 inner product with 1 is 1, and I get a 1 plus EU prime. This in turn is of course nothing else than delta U prime. So I get 1 plus delta U prime inner product between phi of x and phi of x prime. Right. Which is exactly what we had before. Any questions about this derivation here? Yes?
So you're just using direct sum to denote stacking these?
Exactly. Yes. And I'm using tensor products to get to product operations between kernels. Any questions about this? Everything clear? Everybody thinks he can do that for the exam? Any more questions about this?
Is it going to be on the exam?
It could be. I mean, you know, machine learning is going to be on the exam, so I think I was sufficiently clear, right? Okay, good. So, okay, so I guess tensor products are useful. Good. So this is actually something that some people like Pontilli and Miceli and Haldom did before, and they addressed this problem for like 2, 3, 4, 5 tasks, right? And if you have a small number of tasks, then this is of course really easy because you actually explicitly, construct your higher dimensional space. So Dom wrote this nice paper about embarrassingly simple multitask learning where he explicitly duplicates or replicates parameters. You can do that for a tiny number of dimensions, but if you have a couple of 100,000 users, it's less fun. So the problem is, how do we actually keep the dimensionality of that space at bay when we have a lot of data, when we have a lot of users? So this back of the envelope calculation here gave me something like 10 to the 13 dimensions. Now, how do you get 10 to the 13 dimensions? It's actually very easy. Let's assume that I have a not so popular email service, and maybe it only has like 10 million users, right? So 10 million users is 10 to the 7. Imagine that I have maybe 1 million different features that could possibly be relevant. That's not uncommon. Most of those features are never used, but if you take all the different tokens that you could encounter, 1 million happens fairly quickly. And so I have 10 to the 6 times 10 to the 7, and so I end up with 10 to the 13. So if I want to build a classifier in that 10 to the 13 dimensional space, well, good luck, right? So 40 terabytes is kind of what you get if you're frugal and you're only using floats. But basically, nobody will buy you that machine. I don't think you can buy a single machine with 40 terabytes for reasonable amounts of money. Maybe the NSA has one. Okay. Yes?
You only store W, right? You only store the
You only store W, but now the parameters could be, 10 to the 13 dimensional. So how do you get around it without really breaking the bank? Because if you think about it, most of those features are going to be 0 anyway. Most of those combinations will never occur. And most of those things are totally irrelevant. Because, for instance, I personally will probably never use a word in Kiswahili because I don't speak that language, right? Likewise, I will probably, at least right now, so far I have never used Chinese characters in my emails. Again, because, I don't understand them. So it therefore means that a large number of features for me are completely irrelevant.
But you're going to receive emails with Chinese characters.
I might be seeing emails with Chinese characters, so that might actually be relevant, yes. But the point is, most of the features are going to be irrelevant for most people. So how do we fix this? So one thing that people have done is so when they take documents, they would actually first go and build a dictionary of all the words that occur in a document. And then it would map all the words to an integer ID. Right, that's not entirely uncommon. So you could, for instance, take the word mention, and maybe it gets position 1. But then Barney, for him, the word mention and for the user Barney gets at position number, I don't know, maybe 20. Right? And so I get, more and more of those features. Pardon? Okay. So when you perform text classification, you're going to use something like a bag of words representation. I guess we've done that before, right? Does bag of words make sense to everybody? Okay. Any questions about bags of words? Okay. If you actually want to see a real bag of words, come up to the 8th floor of the Gates-Hillman Center. Near the elevator, you will see a literal bag of words with the stop words on the ground. So this is quite a cool project that some former CMU graduates did. So basically, what you have to do is you have to map each word to an integer ID that also compresses drastically the representation, so you're tokenizing. Sometimes you might want to do interesting NLP things, like you might want to normalize and stem and do all sorts of other things to remove various things. Those may not always improve the performance. So sometimes stemming can actually make performance worse, because you're basically removing some of the meaning from the document. And the other thing is, of course, bag of words completely ignores the order of words. So you might want to do more clever things than that, but bags of words isn't too bad. So what you then do is, in this case here, is I'm assuming that I have, the numerical IDs for the words as they occur, and then also the concatenation of user ID with a word being mapped into a new thing. So now my dictionary will have to, provide for a possibly 10 to the 13 dimensional vector. It's a little bit crazy, and nobody can really afford such a dictionary, but just bear with me for a moment. Let's assume I actually had such a magic dictionary. So what I then do is next is I actually take a hash function. So remember, hash functions are things that take arguments and map them into a well-defined range. In this case, they ingest a number, like 20 or 1, and they map it to a new location. So in this case, I'm going to pick, let's say, if this is capital N, this is maybe little n, so this is a much lower dimensionality, and capital N is much larger than little n, into a lower dimensional space, and I just write those entries there. If I get a collision, well, okay, I just add them up. No big deal. We'll see that it isn't a big deal. But then actually, if you think about it, you could just entirely forget about that dictionary part. Because hash functions don't only take numbers, they can take entire strings. So what I can simply do is I can feed the string mention or the string mention Barney into this, right? And this hash function will equally just produce some location as before. The only additional twist that I'm applying is that I'm using also a binary hash function, sigma I, which is going to emit 1 or minus 1. It's basically a 1-bit hash, if you think about it. Okay. In practice, one way of achieving this is, let's say you have a hash function like murmur hash, and that produces maybe 64-bit, and you only need 20-bit, for that vector anyway, because you want to map everything into a million dimensions. Then you can use one of the remaining bits for the sign. It's important not to reuse the same bits that you've already used for that location. So if this is my hash, this is maybe 64-bit, and maybe this is already being used, so this is 20-bit. Then, okay, what would happen if I picked one of those bits here also for the sign? What horrible thing would happen?
I didn't get why you need a sign here.
Okay, so I'll explain the sign in a moment. Essentially, the sign will take care of things being unbiased. I will derive this in a moment. But what would happen if I was to multiply with a sign in a way that is reusing those bits here? So basically, here I have, let's say, for instance, if I want to map only into a million dimensions, then I'll take 20-bit. If I was to use one of the bits that I use for the memory location also for the signs, that would simply mean that any time I map into this memory location, I will pick the same 1 or the same minus 1, right? And I don't want that. I want this sign to be independently chosen from everything else. So I basically pick another bit, maybe here. So we'll see in a moment why this is a very useful construction. So we'll actually prove that this gives us an inner product that is in expectation unbiased. So it turns out that this is actually a very old idea due to Charikar, Chen, and Farah-Colton from 2003. Okay. So they use exactly that in the count sketch. Okay, so let's first think about, why this hashing is useful, and then I'll show you actually how the math works out. So one of the useful things is that I don't need a dictionary. So sometimes when you do, text classification, actually ingesting all the documents, finding a dictionary, and then, building that object is actually the most time-consuming part. You don't need it here. So I can actually use all the memory directly for classification for the parameters. I don't need to have any other clever data structures. I don't need to store anything in memory for any projection because we're projecting onto low-dimensional space here, but I don't need to store anything because this is implicit in the hash function. And the other thing is it preserves sparsity, because if I had, like, say, 10 non-zeros, then in the mapped space, I will never have more than 10 non-zeros. I might get collisions, which will actually reduce the number of non-zeros, but it will never increase it. So now let's actually see whether this is useful in any particular way. Right? So this is exactly the, well, why on earth are we doing this? So the first thing to think about is, well, it actually preserves the inner product. So let's say we have an unhashed inner product w.x, which is just sum over wxi. And okay, let's actually go through this in a bit more detail. Okay. So what happened was, remember, if we map this high-dimensional vector into this lower-dimensional object, we basically, at location I, we compute a hash of I and map it into some location here, and we also multiply it by sigma of I. So this is just a binary hash. So now if I want to know, let's say this bin is called L. Sorry, actually it's called J on the slide, so let's call it J. So if you think about what the value of after this hash map is, it's basically the sum over all I with the property that hash of I equals J xi times sigma of I. Right? That's what happens. This is basically, let's call this maybe x bar of j. So this is really just explicitly writing out what happened. We do know that in expectation, sigma of I times sigma of j is delta ij. Quick question, what are we taking the expectation over here? So we're taking the expectation over all those hash functions. So basically we're treating the hash function as a random variable. But we pick one, we pick also, basically one binary hash, we're picking, a just run-of-the-mill generic hash function, and that's it. So now, another quick question, how can I, let's say I have a really fast hash function implementation like murmur hash. How can I turn this into a distribution over different hash functions? Any idea? So let me just write out the name of this thing. So if I have any hash function h of I, well, this is of course, a very specific hash function. Now, how can I get an entire distribution over hash functions? And I'm assuming that murmur hash, for instance, is very, very good. I can basically do the following thing. I compute hash of I and z, where z is just some random variable. Ideally, drawn from the entire alphabet. Now, what this z does is we know that since it's an ideal hash function, h of I and h of I and z will be independent of each other. Right? So basically, if I know this, I can't do anything with that. And that is all I need. Because now, basically, by having z, it will create a sufficiently random offset that, knowing all the different values of h of I, will help me nothing to infer the values of h of I and z and vice versa. Okay. So, pardon?
You mean solving?
You're effectively salting the hash, yes. So if you've done computer science with hash functions, yes, the security, so you would actually do stuff like this. Yes. So, and I'm just ignoring all those details in here by just saying, well, I'm taking an expectation over those binary numbers. Okay. So this is an extremely useful property because I can now ask, what's the expected value of xj times, let's say, zj, where basically x and z have been hashed in the same way. Well, let's actually write it out. It has nothing to do with that z. Okay. Expect value. And let's just say I'm taking it only over sigma. X bar j times c bar j is just the expectation over sigma of the sum of all I with the property that hash of I equals j xi times sigma I times the sum over all L with the property that hash of L equals j, zj sigma of, cl sigma of L. Now, since I'm taking that expectation, it'll immediately follow that the only time when that term here is zero is it's non-zero is when I equals j, I equals L. So we have delta IL. And so this gives me nothing else than the sum over hash of I equals j xi zi. Now, if I take the sum over all possible j's, this is nothing else than x dot z. Now, if I take expectations over the hash functions themselves, that doesn't actually change anything else. The hash functions themselves come in when you then want to control the variance of that random variable. Because the more bins you have, the fewer collisions you will get and the lower the variance. So variance will go like 1 over a number of bins. Okay. Any questions so far? So can you please speak up a bit? I'm having trouble even hearing you here, and I think you're...
So what is that x?
What is x?
Yeah.
Well, x is, for instance, the email. So x is the thing that we want to deal with. And before that, we talked about phi of x, and I was just lazy, and I referred to that as x. Just because, otherwise it just gets a little bit heavy on the notation.
How did it relate to the taking a hash function of the position?
So the positions are the words, right?
So the coordinates here would be the words, but I could also do that for very different data, right? So I could do that for images, I could do that for a lot of other things, but here it's the bag of words, where it's basically things like invite _ Barney, right? Where this is basically now a token in its own right.
So the coordinates are the word, but what is the content? What is stored in that?
Well, what's stored in there is that the occurrence of let's go through it explicitly because this is going to be easier. So let's say to be or not to be. And that email is sent to Alex. Okay, good. So now what we're going to get is, maybe the word to has position number 2, B has position number 5, or has position 1, this maybe has position number 3, this has position 2, and that's 5. Okay. So we get out of this a vector. So I'm just doing bag of words, which is going to be 1 from this one here, 2 from this here, 3 we have 1, 4 we have 0, 5 we have 2 again. Okay, it's bag of words. Now, if I wanted to do this tensorized with my user ID, then I will get lots of zeros here. This is not to scale because I would run out of paper. And then at some point at position Alex, we would have 1, 2, 1, 0, 2 again, and then we'd have lots more zeros. So that is basically the original vector that I would want to hash. And this vector is in a maybe 10 to the 13 dimensional space. So it's pretty unwieldy. And what I would then do is I would go and let's say this is position 1. So at position 1 I will compute hash of 1. And that's maybe position number 42. And so in my new vector at position number 42, I'll store this. Maybe position 2 is number 1, goes here. Maybe hash of 3 is 1002. Maybe, well, we don't actually need to know what hash of 4 is because it's 0. Hash of 5 might be maybe down here, right? And then I repeat the same game here again for me. Maybe I start at position 1,000,001, and so you'll get the same locations there.
So what do you do when you have a collision? Do you accumulate? Or
Yes, you add things together. That's what I just mentioned before. And that's actually also, this is exactly what we had here. We sum over all the collisions, right? We went through exactly that before. So, and the other thing is that I adorn this with a random sign. So this is basically where you have, sigma of 1 maybe is a plus. Maybe here it's another plus, maybe here it's a minus, here it's a plus. And that's basically what you do to store. So in this case, you would get a 1 here, you would get a 2 here, you would get a -1 here, and you would get the +2 here again. And what I just did is I showed you that in expectation over all hash functions, the inner product is preserved. With it's already preserved just with regard to the random signs, so the sigmas. And if I, in addition to that, take an expectation of another random variable that didn't really matter here, namely the hash functions themselves, nothing changes. However, for the variance, you actually care about the number of bins. Because the larger the number of bins, the more variance you get. Okay. So, now we need to get on with this because we've gone through this in a lot of detail. So what really happens is that basically, since the inner products are approximately preserved, and you can actually prove that they're fairly well preserved by using Chernoff bounds, we can basically keep things that were orthogonal before approximately orthogonal afterwards. It's kind of convenient. So we can do multitask learning. And yeah. Basically, there's a lot of really beautiful theory that you can do with it. And there are basically two Soda papers, one by Kumar, Shalosh, and Dasgupta from 2010, and then Clarkson and Woodruff from 2012, and they actually got a best paper prize for that, for a fairly refined analysis of that property. I'm just showing you the algorithm, but if you want to read up on the theory, it's actually very, very beautiful stuff. Okay. So then, let me show you a little bit the performance that you get with this. So what we did is we basically looked at how well you can classify things in a personalized manner, in an unpersonalized manner, by using hashes and not by using hashes. So the first baseline was that we took an unpersonalized spam classifier, and that just reports to a normalized spam miss rate of 1. Quick question, why do you think I was not allowed to report actual spam error rates? Why would that be a bad thing? So I was working at Yahoo at the time. Why do you think this would be a bad idea?
You wouldn't want to know, or Yahoo wouldn't want people to know if Google had a better rate than Yahoo?
Exactly. Or rather, yes, basically, Yahoo wouldn't want the folks at Google to know whether their spam classifier was better, right? So that's why quite often when you work in a company, you will do all sorts of bizarre things in the end to obscure the actual numerical performance of your system. So if you read papers at Wisdom or dub or related conferences or SIG-IR, quite often industry research will not give you absolute performance figures, but always just performance figures relative to some other system that is maybe also in use, or, okay, basically they'll try to be as vague as possible. And quite often that's a necessity in order to get the results published at all. So keep that in mind when you read such a paper, and don't get too upset about it. Secondly, if you do an internship in one of those companies, which I can only recommend, because you'll learn a lot, you'll basically have to deal with that afterwards when you write up a paper out of your internship. Okay. So this was a rather small data set, about 20 million emails total, 400,000 users. Yes, I mean it that this is a small data set. And basically, what you can see is that if you use, well, about 20 or maybe 22 bits in your hash function, then you're pretty much achieving the same performance as the baseline. So basically, the blue curve is what you get for unpersonalized hashed. Maybe I should pick blue. Right? And so what's going on? Well, if you think about it, well, unpersonalized hash needed about maybe 500,000, maybe 1 million different features. And 20-bit in the hash function mean that you have 2 to the 20 bins, which is about 10 to the 6. And that's why around those numbers here, you get something fairly reasonable. You just are extremely unlikely to get a lot of collisions here. So might be a good idea to just go through balls and bins analysis if you're not very much up to speed on that. Okay. So look at balls and bins. Now, for the personalized spam filter, you get something else. What you can see is that as you increase the number of bins, you actually start outperforming things quite drastically. So you get about 1/3 reduction in basically spam misclassification, and that's a meaningful deal. Now here's the problem though. Unlike most students at CMU, which is totally awesome, who label everything, this is CMU, this is reality. Sorry, goes the other way around. Apologies. That would have been an insult, right? This is CMU. But most of the users hardly label anything at all. So this is number of labels versus number of users, and this is power law behavior. So basically, you guys are just way the exception, which is awesome, but it really stinks that most users don't label stuff. So how well does it work even for those? So what we did is we stratified by group. Basically, how many labels you get per user. And we looked at the corresponding spam classification performance. And what you can see is that those users that label a lot get a lot less spam afterwards going through their spam filter. And those users who don't label much still benefit. So there are obviously two questions here. First of all, how on earth can we even measure something with 0 labels? Well, what we did is we cheated. We basically took that one label out from a user who labeled at least one email. So that way you can get some estimates. The second thing is, why should the user who didn't label anything at all still be able to benefit? Well, actually what happens is it basically removes those users with very abnormal preferences, such as spammers, right? So basically it makes mislabelings also robust because everybody gets his own label parameter vector. So if a spammer decides to go crazy and label a lot of things as ham, that should be spam, well, that affects mostly him and nobody else. So this is similar to how you would deal with a troll on the internet in a news forum. You can't just go and ban him because he'll come back with a new user ID. What you do is you make it so that only he sees his own posts, and then he thinks, well, nobody likes my posts, and then he goes away and trolls somewhere else. And effectively, the same thing here. So the spammers would see that their emails go through, and namely to them and to nobody else. And you can use stuff like that for approximate string matching. I think we're a little bit out of time. Basically, you just can go and generate all possible substrings of a string. And then you basically, use these as features. So the nice thing is that this is only exponential in the amount of mismatch, but not in the alphabet size. Right? You basically just add wildcards and you hash them. There's a lot of other tricks that you can do in order to deal with efficient memory access. There's something called optimal Golomb rulers and so on. So look this stuff up. This is really, really cute. And unfortunately, totally unscalable. But this is basically how your cell phone antennas are designed, and you can use the same tricks for this here. What you can do instead is you can actually use cryptography. And there's not enough time to go into that in a lot of detail. Think about it if you want, and it's kind of fun. So basically, this has a lot to do with systems and still trying to get randomness and then combining things in efficient ways. Okay, so this was maybe a slightly more applied lecture today. After the exam, we will get into optimization and then do Gaussian processes And then after that, it's recommender systems, graphical models, deep networks, learning theory, and so on. Okay. Any questions so far? Let's stop the camera.